All right, we're going to be focusing on two smaller concepts today, something called resonance structures and polyatomic ions. We're going to be applying what we've already learned about Lewis dot structures to each of these. So a resonance structure occurs when we have a Lewis dot structure that includes a double bond that allows for more than one possible Lewis structure that can be written. So the actual molecule that we'll see is going to be a composite of all the contributing resonance structures. So for example, we have SO3. Now, SO3 could have a double bond between sulfur and this first oxygen. It could have it between sulfur and the second oxygen, or perhaps it can occur between sulfur and the third oxygen. All of these are plausible structures for SO3. This true structure is somewhere in between all of these. We take a composite of them. So we start with basically having a single bond between sulfur and each of the oxygens. I've included 2 electrons on each, and then we're going to use a double or dash line to represent the fact that this double bond could be existing between any of those oxygens at a given time. And we'll talk a little bit more about that tomorrow. But this would be, again, a composite of all the possible resonance structures for the compound SO3. Now, Lewis structures for polyatomic ions, these are very similar to how we draw our covalently bonded compounds. However, we're going to be adding or subtracting extra electrons based on the charge, showing and reflecting that change. Now here we have SO3 with a -2 charge. Now one thing remember as a strategy is to make sure that you add up the electrons that are available. So sulfur has 6 plus I have 3 oxygens, which means I would have 24 electrons. However, this -2 charge means I have an additional 2 electrons that I'm going to have to place. So in the end, I should have 26 electrons that I'm going to be filling in. So I'm going to go ahead and start with sulfur in the center. Now this is different than what we did before with our SO3 as a compound. Here we have it as a polyatomic ion. So I'm going to start and go ahead with making a bond between sulfur and each of the 3 oxygens. So it counts for 6 of my electrons, which means I'll subtract it out there so you can see that. I have 20 electrons left. I want to remember apply them to the outer electrons first. So I'm going to go ahead and place 6 around each of the oxygens here. So you can see I have 6 around each, with 6 times 3 gives me 18 electrons that are left. So I have 2 electrons that are left, so I'm going to place those then, the extra ones, on the center sulfur so that sulfur has 8. Now the difference here is because this is a polyatomic ion, I've gained 2 electrons. That means then we're actually going to place it in our brackets and then place the -2 charge showing the gain of 2 extra electrons. And again, before we walk away, you should be able to count that we have 26 total electrons in our structure and that all of them have 8 valence electrons around them, so meaning that we have a correct structure. Now here we have NO2. So again, we have 5 electrons in nitrogen. We have 2 times 6, so an additional 12 from oxygen. That gives me then 17 electrons plus my 1 extra from the -1 charge, so I have 18 electrons to work with. I'm going to start by putting nitrogen in the center and my oxygens on either side. I'm going to start with a single bond between them. So that accounts for 4 electrons, so I have 14 left. I'm going to go ahead and place, to start, 6 electrons around each. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there we go with having 12 of those 14, so I have 2 left. Remember, I'm going to place those on the center. And minus the 2 gives me 2, 0. Now, as you can see, while the oxygens have the correct number, nitrogen does not. So that means I'm going to have to, since I've run out of electrons, I'm going to move these 2 electrons and share them between oxygen and nitrogen. Now that all of them have 8 around them, and I still have the total of 18 electrons. Now remember, this does have a -1 charge, so I'm going to place it into brackets and place the -1 charge on the outside. Now remember, this double bond could exist on either side, so technically we would need to write the additional resonance structure. Okay, so copying this down and simply basically doing a mirror image of it in the sense of we're going to now move the double bond to the other oxygen and place 4 electrons around it, if you can see it on my picture there, keeping the 2 electrons on nitrogen, and then this oxygen is going to get the 6 valence electrons, or unpaired valence electrons. So here again is we're drawing a polyatomic ion of NO2, showing again the resonance structures, the 2 possible structures of this polyatomic ion. Alright, now here I've shown you we're going to do a compound that includes sodium bonding with the polyatomic ion NO3. Here I've already shown you the three possible resonance structures of NO3 with a -1 charge, with the double bond being reflected between the three different bonds between nitrogen and the three oxygens. So if we go ahead and actually draw this complete compound, I'll start by just doing the composite of them. So having the single bond for each, drawing my dashed line to represent the possible double bond that could exist between all of them, and then I'm only going to draw the 4 electrons, which again would change depending on where that double bond is existing. Placing that into the other bracket and giving it the -1 charge. And then Na, because this is a polyatomic ion, the metal is going to ionically bond with the NO3. So we have Na, which is our positive ion, has 0 dots, and that gets a +1 charge because it went from 1 valence electron, which you can find on the periodic table, to 0, so it lost 1. And we can see that following the same rules as before, our total charges add up to 0. So one thing to point out, within the polyatomic ion, we have covalent bonds. And then between the polyatomic ion and the metal, we have ionic bonds. So compounds containing polyatomic ions contain both covalent and ionic bonds. And then finally here I have Li attached to a polyatomic ion, cyanide. We're going to start with our carbon and our nitrogen, starting with a single bond. If I just look at this part, okay, I'm going to see that it's actually Cn with a -1 charge on table E. Carbon has 4 electrons plus the 5 valence electrons in nitrogen plus my 1 additional one from the charge. Means I have 10 electrons to work with. So right now I've taken care of 2 electrons. I have 8 remaining. I could go ahead and put 4 on each to start. So I'm going ahead and taking care of that. So I have 2, 4, 6, 8, 10. So I've taken care of the rest of them. However, neither of them have a full octet. So I'll start off with carbon, getting rid of these 2 and moving it to make a double bond. That helps out nitrogen, but still carbon does not have a full octet. So I'll move an additional 2 electrons so that it has a triple bond, which is the correct structure. However, remember it gained an electron, so it's a polyatomic ion, showing the -1 charge on the outside of the brackets. And then that's going to ionically bond with the lithium ion. So again, we have covalent bonds, electrons shared within the polyatomic ion, but then lithium ionically bonds with that polyatomic ion, and the sum of the charges equals 0. Alright, so that's a little bit about resonance structures and polyatomic and compounds containing polyatomic ions. So go ahead and write your summary or complete the Edmodo quiz, and we'll go over this more in depth tomorrow during class.